any periodic function in terms of sines and cosines, right? You take any function f of x, if it is periodic in nature. Periodic in nature means, right, it should be like this. See, this is a periodic function. Examples of periodic function. Example of periodic function means the graph of the curve remains same throughout an interval. Suppose you take this interval, suppose this is sine 0, 0. This is a sine curve. Sine curve is a classical example for a periodic function. Sine 0 is 0, sine 2 pi is also 0, right? This is sine 90, sine pi by 2. So sine pi by 2 is 1, sine 80, 0, then sine 270, this part is -1. So this is a nice sine curve, right? It takes the value 0, then moves to 1, right? It moves to 1 here, then again it takes the value 0 here and moves to -1, and again goes to 0 here. So totally it moves from 0 to 360 degree, 0 to 360 degree, that is 2 pi degree, because pi is denoted as 180 degree, right? So 2 pi means this is 360 degree. So for any 360 degree rotation, right, from 0 to 2 pi, right, you have a sine curve. Now if you move from 2 pi to 4 pi, 2 pi to 4 pi, right? So what is the distance between 2 pi to 4 pi? Again the distance is same. Total distance is 2 pi. So from 0 to 2 pi, the distance is 2 pi. From 2 pi to 4 pi also, the distance is 2 pi, right? And you see the graph of the curve, it's again same. So this type of functions are called as periodic functions because it takes some representation over a period like 0 to 2 pi, right? Then after for any periodic length of 2 pi, that is from 2 pi to 4 pi or 4 pi to 6 pi or 6 pi to 8 pi, the graph of the curve remains same. The graph of the curve remains same. Not only in the positive interval, it is also in the negative interval also. It is also in the negative interval. That is, this is -2 pi, this is 0, this is +2 pi. So the graph of the curve remains same even from -2 pi to 0. So -2 pi to 0, what is the total length of the interval? Total length of the interval is 2 pi length. 2 pi length. So as well as length is concerned, from 0 to 2 pi or -pi to 2 pi, the length of the interval, that is -2 pi to 0, the length of this interval, I think you know the length of the interval. Length of interval means, suppose if it is 6 comma 8 is the interval, then what is the length of this interval? Length of the interval is 2. So length of the interval is nothing but 8 minus 6, right? The total length. So when you say whatever may be the length, whether it is the positive side or negative side, the graph of the curve remains same, right? So this is the basic of periodic function. And this follows, you can see any, even you can see in ocean, the waves are follows a pattern. The waves are follows a pattern. So thermal wave is there, the electrical waves are there, magnetic waves are there, sound waves are there, right? So whatever may be, it follows certain pattern. So that is called as the periodicity of the curve, otherwise the periodicity of the function. So what the Fourier did is a very simple thing. He just try to write any periodic function, right, in terms of sines and cosines, because sines and cosines are already known functions, and we know the properties of sines and cosines. They are periodic in nature, right? So if you are able to write any, if you are able to give a representation of any function in terms of sines and cosines, then it is easy to study that function, right? So Fourier series is a representation. Fourier series is a representation. So that here you can see the word a representation in the form of trigonometric series. So Fourier series is nothing but giving a representation of any function f of x which satisfies certain conditions. Not all functions. It should be periodic in nature, that is must, and it also satisfies certain conditions. Then that function can be written in terms of sines and cosine, and this is called Fourier series, right? Now I'll tell you what is, so this is the basic idea of Fourier series. Now I'll tell you the, so periodic function you already know anyway, right? I just go through it, right? So periodic function means sine theta is same as sine theta plus 2 phi. Very simple, right? Sine theta is same as sine theta plus 2 pi. What is the meaning of this? Suppose if you want to find sine 30, suppose if you want to find sine 30, sine 30 is same as sine 30 plus 2 pi. Sine 30 plus 2 pi, because after 2 pi rotation, 2 pi means after 360 rotation, 360 degree rotation, you are coming to the same place, you are coming to the same angle. So sine theta, right, whatever it value it takes, the same value it takes for sine theta plus 2 pi. It is same true for cos also, right? Cos theta or cos x is same as cos x plus 2x, x plus x plus 2 pi, x plus 2 pi. In general, you can see any function f of x, it, and its value is same for f of x plus t, where t is the periodic length. So here f is nothing but your sine function or cos function, t is nothing but your 2 pi, right? So in general, you can write f of x equals to f of x plus t, means you take any function, if it is periodic in nature, the function can be written as f of x is equals to f of x plus t. So here f is a function. Which function? You can take it as a sine function, right? And x is the argument, so that you can take it as theta. And this capital T is nothing but your 2 pi. So it is like f of, f means sine function. So this function x is theta, that is same for again function x is theta plus the periodic length out after which period the graph of the curve remains same. That period is called as, in general it is called periodic length of a periodic function capital T. But anyway, right, here in general they are following the periodic length as 2l, the periodic length as 2l in Fourier series, where l is the half of the length and 2l is the total length. They, in place of t, they use 2l usually in Fourier series. Even in your reference book in Veera Rajan also they uh, put 2l, right? But in this book what are we are learning through online, right, they are taking that l equals to pi, no problem, because we are only discussing about sines and cosines. So they are taking the periodic length as 2 pi, but in general we can define it for any 2l, but here in this book they define it for 2 pi. But anyway, most of the problems we are taking l equals to pi, we are taking the l equals to pi. So whether we are defining the function in the with periodic length 2l or periodic length 2 pi, right, both are mathematically same, both are mathematically same. So don't confuse why sir explained in offline class length is 2l, but here sir putting 2 pi, right? Because even you can say in this formula, those who are attending offline classes know I put c to c plus 2l here, c to c plus 2l, and then I here put n pi by l, right? So that is okay, but in place of l they put pi. In place of L, they put pi, so that the formula looks like in a nice manner, and even the Fourier series also look like in a nice manner. But anyway, they take this assumption here and they start doing problem. But in general, it can be defined for any interval from C to, that is C is the constant starting point and C plus 2 pi is the ending point. So it is an interval like this, C comma C plus 2 pi, like so in this interval only the function defined, and it is also periodic in that nature, right? C comma C plus 2 pi. C may be 0. If C is 0 means it is C 0 comma 2 pi. Or if C has some value means, so you can get that interval. So in that interval the function f of x is defined, right? Now you are able to write the function in terms of sines and cosines, in terms of sines and cosines. So this is the Fourier series representation, right, for the periodic functions. Now, two things you may ask, sir, uh, whether it is possible for all periodic function. No, periodic function is a necessary condition, but apart from that, it has to satisfy some other conditions. Then only you can write the function in terms of sines and cosines. Right? First, I will tell you the condition. Then I'll come back to the definition and the formula. So these are two formulas you have to remember when you do the problem. Right? Okay. So that conditions are called as Dirichlet conditions. Right? So you can see in the screen. Right? Dirichlet conditions. The three conditions given, right? F of x should be periodic, that is must, right? So, and it should be single valued, right? But anyway, once you say it is periodic, automatically you can understood that it should be single valued. It should be single valued because if it is not single value, if it is not single valued, it won't be periodic in nature, right? So, single valued means, right? You can draw any graph of the curve, it should be like this, but not like this. So here there's a loop is there. So when you see the loop, right, you take this point, right? Suppose this is some x naught, then the corresponding function value is this, as well as this, as well as this. So for single f of x naught, it has three function values. It has three function. But if you say here, suppose you take this is x1, then the corresponding y coordinate is f of x1. So here for x1 only one f of x1 is there, but here for x naught, here also it touches y axis, here also it has some value, here also it has some value. So for this type of loop function should not be allowed, right, in Fourier series. And next one is called the piecewise continuous function. So if it is a continuous function like this, then it is okay. If it is not continuous, at least should be piecewise continuous. Then you may ask, sir, what is piecewise continuous? So the word itself tells pieces means you can see like this. So here is one piece is there, then some break is there, then another piece is there, then some break is there, then another piece is there. So these pieces represent some function f of x. The function is continuous except at some points. These are only single point, not in interval, not even interval, right? So whatever the thing here I mentioned in green color, only at that particular point the function is not continuous. The function may be it's not at all defined in that point also, right? But at all other points here in the red line, it is continuous. Then suddenly it is not continuous at a particular point, then it is continuous through an interval that is represented by blue line. Then suddenly at some point it is not continuous, then again it was continuous. So it is like cutting a rope in pieces. So when you cut in a row into pieces, pieces are looks like continuous, but there are some cuts are there, right? So this type of functions where the function is continuous everywhere except a finite number of points here and there, right? So in that case, also you can able to find the Fourier series, right? With finite number of discontinuities, right? So if your function is a continuous function, then okay. If the function is not continuous function, at least it should be a piecewise continuous function. Then only you can able to find the Fourier series of the function f of x. And finally, f of x has at most finite number of maxima and minima. Then you may ask, sir, what is the meaning of finite number of maxima and minima? So you know local maxima, local minima. Whenever you can draw function, a curve like this, the function takes some maximum value, then it comes down, then it goes to some low value and comes up, and then it takes a maximum value and comes down for low value. So for every finite local interval, you can find some maximum value and some minimum value, right? So it is always possible for, if you take this interval, in this interval, this is the lowest value, this is highest value. So these are called as local maxima and minimas, right? So if maximas and minimas are there like this, then no problem. But it should not be infinite. Infinite means, right? Suppose a function is like this. So what happened? You're also going up and down, up and down, up and down. But infinite number of times it goes up and infinite number of times it comes down. So it has infinite number of maximas and minimas, right? Even a small interval, even a small intervals. But we should have only finite number of maximas or minimas in the interval where the function is defined, right? So one thing you should remember, the function is not defined from minus infinity to infinity. It is defined only from c to c plus 2 pi. Then you may ask, sir, what happened whether function is not there in other place? It is there. But once you give the representation for c to c plus 2 pi. For example, for sine curve, if you know the function value from 0 to 2 pi, for sine curve, if you know the function value from 0 to 2 pi, then 2 pi to 4 pi, no need to define. We himself know because of the periodic nature, definitely from 2 pi to 4 pi, the curve is like this. From 4 pi to 6 pi, the curve is like this. So there is no need, the function, there is no need to define for the entire interval. It can be defined only for the interval, right, with a periodic length, right? Once if it is defined for the with periodic length, we can extend the function both in the left hand side as well as in the right hand side without altering the periodicity of the function, without altering the periodicity of the function. So if you know the sine value from 0 to 2 pi, right, then we can automatically extend that value for the sine curve from 0 to 4 pi. Again we can expand the value of sine curve from minus 2 pi to 0. So all these things are possible because the given function is periodic in nature, right? So all these three conditions are called as Dirichlet conditions. So all these conditions are called as Dirichlet conditions. You can see here the word. So a function should satisfy all these Dirichlet conditions. Then only you can find the Fourier series. Then only you can find the Fourier series representation. Right. So now we come back to the Fourier series representation, right? So you can see here, you see some cos, originally it is cos n pi by L, sin n pi by L, but because L equals to pi here, so they put L equals to pi cancel, it is cos nx and sin nx. But in some book you can find like this, n pi by Lx instead of sin nx, right? But here they are considering this L equals to pi, so that here if they put pi and then cancel this pi and this pi, and they simply write sin nx, right? But mathematically it's no problem, it's correct only, right? Because they define the function c to c plus 2 pi. So for this definition, this representation is correct only. But you may ask, sir, cos function, sin function, we already know. Whenever x is given, we know the value of cos function, sin function. But how it differ from function by function? Suppose some f of x is defined and is represented by cos x, cos 2x, cos 3x, right? Suppose some other curve is there, g of x, some other curve, or some f1 of x is coming. Then in that manner, which one will change? Because cos x, cos 2x won't change, and cos values also won't change. It takes a value from -1 to +1. But but the functions you can't expect it takes only value from -1 to 1 plus 1. It may be periodic in nature, but it may go to any value. So here, what the ultimate thing we have to find in order to find the Fourier series? The ultimate thing is cos nx won't change, sin nx won't change, but the coefficients here, that a naught, an, and bn, these coefficients only will change depending on the change in function. Suppose f of x is some x square, then you have some representation. Then f of x equal to x cube, then you have some other representation. But how the representation change? Cos x, sin x won't change. Only the findings of an and bn will change. So throughout the Fourier series, throughout the Unit-2, only thing you have to find for all Fourier series problem is these two things, ans and bns. They are called as Fourier coefficients of the function f of x. So if you know the Fourier coefficients by evaluating these integrals, then you can directly substitute the Fourier coefficients here in the Fourier series directly. So this is a standard representation. This is a standard representation. So in this standard representation, what you are going to find, in this standard representation, you have to find an and bn using these formulas or in representation, and then after finding a and b, and you have to substitute that whatever you are getting here, then that is called the Fourier series. That is called the Fourier series, right? So now we will see, right, how the definition of Fourier series, right? So here they give the definition of Fourier series for finding an as 1 by pi. So pi is nothing but the total length is 2 pi, pi is half of the length. C to C plus 2 pi is the place where the function is defined, where the function is defined. And f of x is the function given. Cos nx we know, cos function dx. So if you evaluate this, then we get an in general, an equals some 1 by n square or 1 by n cube or something will get. And then you have to substitute that here. Similarly, you have to find bn. What is the change between a and bn? Only one change. In place of cos, sin will come. Apart from that, all other things are same. All other things are same. You may ask, sir, why they are writing a naught separately? Because in the derivation that some constant is there with a naught, so that they are writing a naught separately. So even if you find a naught separately by putting n equals to 0 here, cos 0 is 1. So in that case, 1 by pi c to c plus 2 pi f of x, this becomes 1 dx. That is the value to find a naught. And then an you can directly find using this formula and bn here. But you can't find b naught. You may ask, sir, here n varies from, here n varies from 1 to infinity. Okay, because we already found a naught. Now this is a1, a2 up to a infinity. And here also b varies from 1 to infinity. But there is no b naught. Where is b naught, sir? You may ask. Because b naught doesn't exist. Why? Because when you see this thing, I will expand like this. Wait. Right? When you see this representation bn, when you put n equals to 0 here, right? This is f of x. This is sine n equals to 0, right? But sine 0, 0, you know. So b naught is always 0. So you can find a naught, an from n varies from 1 to infinity, right? But bn is only for 1 to infinity, not for 0. See, here 0 is there for an, but for bn it is not there. All right? So, and the formula is this only, straightforward formula. So, only thing you should know some basic integration methods in order to solve Fourier series problems, right? So, now we will see the problems one by one. I hope, right, you understand the definition of Fourier series, right? And what is the aim to find the Fourier series? The aim is, the ultimate aim is simply how to evaluate or represent the given function in terms of sines and cosines, right? So up to this, any problem? I understood, because now I am going to the problem. Up to this, okay? Can we proceed?
Yes, sir.
Okay. Right. So here the expand the function f of x, x into sin x. It is defined in the interval 0 to 2 pi in Fourier series. Right. So here remember it is right. the- Already a sin x is there. Right. So already the half of the function in trigonometric form. But you can see the other half, that is x. It is algebraic function. Now you have to express the entire thing in terms of sines and sines and cosines, right? So before that, I will tell you certain things about some properties of sines and cosines, because that will be very, very much helpful to you when you solve the problems, right? So here I just put the whiteboard, right? I just ask you certain simple questions. What is sine 0? Anybody say?
0.
0. What is sine pi? Sin pi. Sin pi means this. Sin 0, sin 90, sin 180. So what is sin pi? Sin 0, this is sin 90 degree when it touches 1. And then it is sin 180 degree. What is sin pi? Now you tell. Anybody?
1, sir.
No. Sin pi is again
-1.
not -1, 0, 0. See, this is 180 degree, man. Where the curve touches. It touches the x-axis. X-axis means sin pi 0. Right? Sin pi 0. But sin 90 is 1. Similarly, sin 270 is -1. Sin 270. Sin 270 means pi plus pi by 2. That is sin 3 pi by 2 is -1. Sin pi by 2 is +1. Sin 3 pi by 2 is -1. Right? Again, if it goes to here, right? When it touches 2 pi. When it touches 2 pi. So again, when sin 2 pi, it becomes 0. So for every 180 degree, it touches 0. So in general, we can write sin n pi, where n is any in natural number. Then sin n pi is always 0 for all values for all values of n from 0 to infinity. So one thing you should know, sin n pi 0, right? So keep this in your mind. Now we go to cos 0. What is cos 0?
1.
Cos 0 is 1,
1, 1.
right? Then what is cos pi?
Sir, 1.
No, no, no. See, again I draw the graph. Cos 0. Cos 0 means when x is equal to 0, f of x value is 1. Then cos 90, 0. Then cos 180,
-1.
cos 180 is -1. Right? Again, if it goes to 360 degree, cos 2 pi, what will happen?
1, sir.
Cos 2 pi is plus 1.
1.
So here you can see some alternative of 1 and -1. Cos pi, cos 3 pi, cos 5 pi, cos 7 pi are all -1. Cos 2 pi, cos 3 pi, cos 4 pi are all +1. So whenever n is even, it takes the value +1. Whenever this coefficient, whether it is 3 pi or 5 pi or 7 pi, whenever it is odd, it is -1. So this can be written in general as cos n pi. Cos n pi is equals to -1 the whole power n. How? When you put n equals to 1, you put n equals to 1 here. -1 the whole power 1 is -1, right? So cos pi, cos n equals to 1 means it is cos pi. So it becomes -1. But when you put n equals to 2, right? Cos 2 pi, then -1 the whole square. -1 the whole square is +1, right? So cos 2 pi is +1. But when you take cos 3 pi, cos 3 pi means -1 the whole power 3. So again it become -1. Again it become -1. So in general we can write, cos n pi as -1 the whole power n and sin n pi as 0. So sin n pi 0, cos n pi, take alternative value. So it is -1 the whole power n. Whenever n is even, it is value is +1. Whenever n is odd, its value is -1. Right? So you have to keep this in your mind before moving to the problem. Right. So as I told already, you have to find A naught, AN and BN. Right? So formula to find A naught. You just see the formula is here. Right? 1 by pi. Okay. C to C plus 2 pi. But here in place of C, 0 is there. So this is C plus 2 pi. Right? So lower elemental is 0. So here also they started with 0. Upper limit is 2 pi. Right? So now what you have to do, you have to evaluate this. But what is f of x? F of x is sine x into sine x. F of x is x into sine x. So you simply substitute here x into sine x, and then we have to evaluate. So here a naught is 1 by pi 0 to 2 pi. F of x is there, and in place of x we substituted x into sine x, right? So now we have to integrate this. For that, you know one methodology called as integration by parts, right? Integration by parts, but that is integral u dv is equals to uv minus integral v du. This is called integration by parts. Even in school or in first year, you may study this integration by parts, right? But here, integration by parts is okay, good. But here, if it is only x sin x, it's okay, manage. You can get only like this. But if it is x square sin x or x cube sin x, then it is very difficult to apply integration by parts, because each and every time you have to apply, right, again and again. So that I will just tell you one simple formula, right? So this formula you try to mug up. This formula is called as Bernoulli's formula. Same thing, u dv can be written as u, same u, v1. v1 means the same thing. If integrate dv, you will get v. Here also, if integrate dv, you will get v1. u v1 minus u dash. U dash means whatever you are getting, you have to differentiate one time, you will get u dash. Then if integrate v2, v1, you will get v2. Right? So differentiation of u will get you u dash. Integral of v1 take you to v2. Then plus u double dash. So first u dash, now u double dash v3. So how it look like, right? I'll write it in a whiteboard, right? So integration Bernoulli's formula is look like this: u dv is equals to u v1 minus u dash v2 plus u double dash v3 and so on. Then you may ask, sir, where it ends, because u dash and this alternative signs you should be remember, right? Plus minus plus, again it should minus will come, then u triple dash v4 will come, and will keep on going, right? So it is you have to remember, but you may ask, sir, where to stop. That I will tell you when you solve the problem. But try to remember this formula: u v1 minus u dash v2 plus u double dash v3 minus u triple dash v4, right? So you take one thing as u, another thing as dv. You have to keep on differentiate u, and then you will get u dash, u double dash, u triple dash. Similarly, whatever you are taking as dv, you have to integrate. You will get v1. Then integrate v1, you will get v2. Integrate v2, you will get v3, and so on, right? So now using this, we are going to solve the problem. We are going to solve the problem. Then you may ask, sir, which one I take it as u, which one I take it as dv, right? So there are two functions. One is x, that is algebraic function. Sin x is a trigonometric function. So I always choose the algebraic function as your u, because when you write a Bernoulli's formula, after some representation, after some times you differentiate, the function should become 0. Then only this expansion become a finite one. Otherwise, it goes infinitely. So whenever you take the polynomial as your u, even here also you can say, take u is x, right? U dash is 1. See here u dash. This 1 is nothing but u dash. Then u double dash automatically 0. U double dash automatically 0. Once u double dash automatically 0, what are the things associated, vi is associated with that also become 0. So here nicely you have only u v1 minus u dash v2, right? Because u double dash is 0, so there is no need to find v3. Remember, whenever if you differentiate a polynomial, the power of the polynomial diminishes and it becomes 0 after some time. That only we need, right, when we solve this type of problem. right? So here they take u as x, that is here, then dv as sin x dx, dv as sin x dx, right? So x they put as it is, u, then v. V means integral of sin x. Integral of sin x, you know, that is pi times cos x. So this is uv1 minus u dash. U dash means whatever u here, that you have to differentiate. So differentiation of x is 1. So that is 1 into v2. V2 means whatever here in v1, that you have to integrate. So minus sign as it is. In minus integral of cos is plus sign, not minus sign. Integral. So integral of cos is plus sign. So minus minus as it is, this become plus sign. Right? So now after applying the Bernoulli's formula, we can apply. So this is called Bernoulli's formula. After applying the Bernoulli's formula, we can substitute the limits. Right? But before substituting the limits also, we have to take care of certain things. Right? Just now I told sin n pi value always takes the value 0 and cos n pi value takes the value minus 1 the whole power n, right? So whenever n is even, that is cos 2 pi, cos 4 pi, cos 6 pi, or right, all takes the value 1, and cos pi, cos 3 pi, cos 5 pi, all the value takes the value minus 1, right? Okay. Am I audible? Because here raining is here, so that some high sound is there. Am I audible to you, all of you?
Yes,
Yes,
sir.
sir. Yes,
Okay.
sir.
Because raining heavily here, right? So since sin n pi is always 0, so even if you put the upper limit here, sin 2 pi, the term becomes 0. And sin 0, lower limit, then also becomes 0. So the sin term won't comes whenever the limits are 2 pi and 0. So there is no need to put the limits itself. Automatically it becomes 0. Right? So only thing we have to put the limits only for cos terms. So here you put here upper limit x equals to 2 pi, right? This minus sign is here, then cos is here, then again you put x equals to 2 pi upper limit, right? And sin 2 pi, you know, 0. Sin 2 pi, 0, right? And then the lower limit. When you put the lower limit, x is equal to 0. So I think this point is okay. I think this point is okay. By substituting x equals to 2 pi, you will get this. But when you substitute the lower limit x equal to 0, even for the cos term, cos 0 is 1. But when you put here x equal to 0, that 0 into 1 become 0. Right? And sine already told it is 0. So only this term comes into the place. Right. So here, what is cos 2 pi? Cos 2 pi takes the value 1 because 2 is the even number. So it takes the value 1. So upper limit up in the numerator it is minus 2 pi, denominator it is pi. Then we cancel pi, and minus 2 is the value for a naught, right? Not for an, this is for a naught. Why you are finding a naught separately? Certain things are there in the theory, so that they are finding it in a separate manner, right? So you also at your level you have a formula, nice formula for a naught, because for a naught there is no cos, there is no sine. Simply you have to integrate f of x. But for an you have to add that extra term, that is cos nx. You have to add that extra term cos nx, right? So and then apart from that everything same, whatever here x sin x, the same x sin x is here, 1 by pi everything is there, but extra thing is cos nx. Now how to evaluate this, right? So here the main problem is, right, not the concept, because concept is very simple and formula is also very simple. The thing is you should know basic integration methods and also some trigonometric formulas, right? So for example here you can see there are three functions are there. X is one function, sine is another function, cos is another function. So here even you can't use UDV rule, because for UDV rule you need only two functions, but here we have three functions. So what they are doing now, they are changing here into a nice representation using cos A sin B formula, right? So here they take cos A sin B formula, that is cos nx, we call it as cos A, and sin x we call it as sin B. You may ask, sir, why they take this as A, this as B, right? Because it has the extra representation n. So when we add nx plus x, nx plus x, right? Then it is easy to write n plus 1 of x. Easy to write n plus 1 of x. And one more thing, when we subtract nx with minus x, right? Then also, if you write like this, then it looks nice. Otherwise, you have to write 1 plus n or 1 minus n. That won't be a nice one. So that they use this formula: 2 cos a sin b. That 2 cos a sin b is sin a plus b minus sin a minus b. So nx plus x minus nx minus x, right? So here when you see thing, right? Now what is the only change? Now previously these two trigonometric functions are in product. Now they are in the what we can say summation, or is in difference. Now you can take this x inside, that is x into sine x plus x separately. That is the first integral, and then x into sine n minus 1 of x. Then x into sine n minus 1 of x. So you have two integrals, one with x into sine, this is n plus 1 of x, n plus 1 of x. Similarly, second one is x into sine n minus 1 of x, right? Why we are writing like this? Because if you write like this, now we can apply the Bernoulli's formula, whatever we have applied previously. What we applied previously, x into sine x, right? So here x into sine n plus 1 of x. So again the same Bernoulli's formula, you take this as u and you have to take this as dv. This as dv. So integral of sine is minus cos. N plus 1 of x is like a cos ax divided by a. So this n plus 1 y comes because we know integral of sine ax is minus cos ax divided by a. So that a is nothing but your n plus 1. That a is nothing but your n plus 1. So this minus cos ax by a. So n plus 1x by n plus 1. Right? So in the same manner, here also you have to write as sine, this x is here, sine n plus 1 by n plus 1 of x square, right? How it comes? Very simple. Again, Bernoulli's formula, right? So this is u, this is v1, and this is u dash. So integral of, differentiation of u is u dash, that is 1. Now integral of v1 is v2. Integral of v1 is v2. So if you integrate minus will come. Integral of cos is plus sine, right? So again you have to take another n plus 1, the denominator. Already one n plus 1 is there, but when you integrate this function, right, again, then you will get cos becomes sine. Another n plus 1 comes in the denominator. Already one n plus 1 is there, so it becomes n plus 1 the whole square. N plus 1 the whole square, right? So it is something like u v1 minus u dash v2. Now plus u double dash. Since u dash is 1, u double dash is 0. U double dash is 0. So there is no need to find v3. There is no need to find v3. So we stop here. So this is the formula by evaluating x into sine n plus 1 of x using the Bernoulli's formula. Similarly, x into sine 1 of x can be used by this representation, right? But the idea is same, uv1 minus u dash v2. Only thing is here sin n plus 1, so n plus 1, n plus 1. Here sin n minus 1, so that is n minus 1, n minus 1, right? So all these things are simple integration methods, integral methods. But anyway, I'll explain you step by step. So again, right, now you have to be very, very clear, right? Sine term we don't take. Whenever sine 0 comes, sine 2 pi comes. Because sine 0 also 0, Sine 2 pi is also 0. So sine terms we don't bother. Whether it is n plus 1 or n minus 1, whatever it may be, no problem. You have to only taken care of the cos terms. So when you put the upper limit x equals to 2 pi, here 2 pi minus cos n plus 1 of 2 pi. So here 2 pi cos n plus 1 of x is 2 pi divided by n plus 1 divided by n plus 1. And then here sin n plus 1 of x and in place of x 2 pi n plus 1 the whole square, right? So here we don't bother about sine terms, we are only bothering about cos terms, and in that also we are substituting first 2 pi first, and then now upper limit over minus the lower limit. What is the lower limit? Lower limit is x equal to 0. When you put x equal to 0, automatically, right, this term gone. Even though cos 0 is 1, this term will gone and this term also will gone, right? So now you have a nice representation for 2 pi cos n plus 1 of 2 by 2 pi plus n plus 1 of 2 pi by n plus 1 the whole square, right? N plus 1 the whole square, right? So this is for this. Now you have to do the same thing for this second one, right? The same thing for the second one, right? That is denoted here, right? That is denoted here, right? So whatever here n plus 1 is same thing for n minus 1. So apart from this, everything same. Here minus sign is there, here plus sign is there. Here n plus 1 2 pi, here n minus 1 2 pi, n plus 1 2 pi, n minus 1 2 pi, right? Okay, so now after substituting the limits, we have to put the values for cos, right? You already know cos n pi is minus 1 the whole power n. Cos n pi is minus 1 the whole power n. But we know one thing. Whenever n is even, whenever n is even, right? Whenever n is even, this term become 1. Suppose cos n equals to 2, cos 2 pi, then this is minus 1 the whole square, then become minus 1 the whole square, right? Then it becomes plus 1. Similarly, when n is 4, that time also the value is 1. So I already told you, whenever n is even, right, the value is always 1. And you can see here n plus 1 of 2 pi. We don't know what is n. So that we don't know what is n plus 1. But we know one thing, n plus 1 is a number. It may be odd or it may be even. But if you multiply that number with this number 2, then automatically n plus 1 times 2 becomes a even number. Because when you multiply odd number 7 with an even number, you will get an even number. Suppose for 7 into 2, 14, it's an even number. Similarly, if you multiply odd number, even number with even number like 6 into 2, 12, again that is the even number. So whether n plus 1 is even or not, when you multiply that number with 2, that value always become 1 because of the definition. So that only they are putting here cos 2k pi is always 1, right? Whatever may be the k may be positive or negative, sorry, k may be odd value or even value, odd number or even number, but 2k is always a even number. 2k is always a even number and it takes the value 1 always. Okay, here also the same thing, 2 pi is there. So they take this value as 1. So if this entire value become 1, they have only minus 2 pi. And here if we are also the entire value become 1, here the value is 2 pi comes. Here the value is 2 pi comes. But don't think both are cancelled out. The denominator is different. Here n plus 1, here n minus 1. Then if you do the cross multiplication, right, and nicely you will get a representation like this. 2 times n square minus 1. We ask sir how it comes. Very simple. When you do the cross multiplication like this, right? Here plus 1 is there, plus of plus 1 is there. So 1 plus 1, 2. But that n values are cancel each other because here n is plus, here n is minus. Right? I think you understand. So this becomes 1 plus 1, 2, and this is a plus b, the a minus b formula. So it is n square minus 1, and then this minus n and this plus n cancel out each other. So that an as the representation like this. Right? An as a representation like this. But still it has one single problem, because when you see this representation an, right? When you put n equals to 1 in the denominator, a1 become 2 by 0, right? Because n equals to 1, n square is also 1, 0. So it tells a1 is infinity. If a1 is infinity, means a1 is nothing but the coefficient of cos x. So if one, even a single constant become infinity, then entire function become infinity. But the function is not an infinite function, it is a finite function. So in that case, what we have to do, right? So we can write this an, and we can say this representation is valid from n varies from 2 to infinity. It is not valid for 1, but it values valid for n varies from 2 to infinity. Right? Then how to find a1? Again, we come back to the original formula. What is original formula? an. An means in place of n, I put 1. 1 by 2 pi, 0 to 2 pi, f of x, cos nx. So in place of n, I put 1, cos x. Right? F of x is x sin x. Now you integrate this in your usual manner. You know, sin theta cos theta is sin 2 theta. Right? Otherwise, you can again use cos a sin b formula, sin a cos b formula. You will get this. Again, same Bernoulli's formula. U v1 minus u dash v2. Right? Again, same thing. You have to substitute the limits. Then you will get some number minus 1 by 2. So from this we understand, right, how to find AIs. That is A0 and ANs. The same thing is for BN also. Only one change is, right, in place of cos nx, sin nx will come. Apart from that, you have to use the same type of trigonometric formulas. Same type of you have to split. The same type you have to do u v1 minus u dash v2. All these things you have to use, or you have to substitute the limits, and then you find the value for bn, right? Value for bn. So it looks like a little big one, because previously this is 16 mark problem, but nowadays you have only 10 marks in the university examination. But in cat 2 you have a 16 mark problem, right? I will explain, tell you what is the pattern for that. I think even the department itself will publish it, right? So we have 5 2-mark questions, and one either or choice 6-mark question, and another either or choice 16-mark question, and finally another either or choice 16-mark question. So totally for exam for 50 marks. So for that, this type of 16-mark problems they may ask, right? But here the working procedure is same as for an. Only thing is, in place of cos, sin is there. Apart from the, according to that, you can do, right? Here also you may ask, sir, why they're putting b1 separately? Because when they found bn, right, they get bn representation like this. But again, the same problem, it will not work for n values from n equals to 1. Not values for n equals to 1, right? Not valid for n equals to 1, because when you see here, this and this cancelled numerically, and this cancelled numerically. So it looks like 0, and look like bn is equals to 0 for all n, right, when you solve the problem. But this representation is not valid for n equals to 1. So other you can say bn equals to 0 for n varies from 2 to infinity. For n equals to 1, they are finding separately, and then after finding separately, that is b1 equals to pi. Finally, they have to substitute everything in the original Fourier series. So what is the original Fourier series? A0 by 2. What is A0 value found? A0 value found as minus 2. So that minus 2 by 2 is minus 1. Then we found A1 separately. A1 separately, right? See here, A1 is minus 1 by 2. Minus 1 by 2. So they put A1 separately, right? Minus 1 by 2. And what is the coefficient? For an, coefficient is cos nx. So for a1, coefficient is cos x, right? So after substituting for a0 and an, all other things can be represented in general manner, because that this representation is no problem for n varies from 2 to infinity. So For an they find this, and then they multiplied with the cos nx, right? So up to this a naught and a n's over, up to this a naught and a n's over. Then what about bn's? For bn's, we already know bn's becomes 0 except b1, except b1. So this entire infinity series become 0 from 2 to infinity. Only the first term. What is the first term? b1 into sin x. That is the first term in this infinite series. So all other things become 0. So they take only b1 and sin x, right? And b1 value is pi. So pi into sin x, pi into sin x. So here what they are doing now, they are not solving anything. They're simply substituting in the Fourier series wherever a naught is there. Whatever they found a naught, they simply putting here. Similarly, whatever an they are putting here and bn they are putting here, right? And finally, this is the Fourier series representation for the given function, right? So I take a little bit, some 10 minutes more time, because we can't do it in different classes, because a single class I have to explain, then only you can understand. But still the problem is not over, because when you see the problem, they are asking two things. One thing is find the Fourier series of the function, right? And hence they are asking deduce the infinite series. So after finding the Fourier series of the function, using the representation of the Fourier series of the function, you have to evaluate, you can evaluate certain infinite series like this using the Fourier series. But as I already told, the real application of Fourier series is in the wave theory. It is in the wave theory. But mathematically, we can use that Fourier series representation to evaluate certain infinite series, right? So that we can see in the next class, that is tomorrow's class. So all of you please attend tomorrow's class without fail.